Okay, folks, so continuing along, we're going to pick up right where we left off in describing the vertical transition or Frank-Condon principle and talk about how this relates to the vibronic structure of a molecule. So you might think, what is that word? Vibronic. So that means the vibrational and electronic structure. So vibrations and electronic transitions, because hopefully what we can appreciate now with this Frank-Condon principle, those two things are intimately coupled. And so here's showing you a different picture for what we might see in a spectrum. So this is a spectrum turned on its side. And we can see here now the most intense part of that spectrum, in other words, the lambda max, occurs where we have the strongest overlap. So again, we've got this ground vibrational wave function that looks something like this. And at these turning points here, our wave function will be the most intense and fall off and get more intense again at the turning points. And we can see these features here in this UV-Vis spectra are related to those vibrational energy levels, in the case of these vibration levels being well separated. So let's look at a few molecules to tease this out. So here are the potential energy surfaces of O2. Okay, so here we can see X marks the ground state, the ground triplet state. Then we've got the A singlet state and the B singlet state. And it's worthwhile to note that this AA, those are marked as atmospheric absorption bands. And we would observe those in the visible spectrum if it weren't for the fact that that's a triplet to a singlet. So those are not observed. However, we can see these named bands, the Hertzberg and the Schumann-Runge, those are observed bands because those go from triplet to triplet. So I want to focus in on particularly the Schumann-Runge band here. And I've converted these energies, so this is 579 kilojoules per mole. We can convert that over to what that would be in terms of a photon, and that would be equivalent to 206.7 nanometers. And here we have the oxygen absorption spectra given by its cross-section on the y-axis. And you notice here we have all of these features. Well, these are all related to the vibrational energy levels, those individual peaks. And we can see that here by noting, I'm going to change my color. If I do this vertical transition and I go all the way up here, I'm going to get myself somewhere like near the edge or somewhere close to these vibrational energy levels. And you might notice that we don't have perfect overlap with them, and that's why these cross sections are relatively small cross sections. So we do see these individual vibrational levels being resolved between 204 and 180 nanometers. And as you can see right there, right on this scale, that spans this range right here. So really what we're seeing in the spectra is the B triplet sigma U minus state and all of its respective vibrational levels. But you also notice here that we've got these individual peaks within each vibrational level. Those are our J transitions, our rotational transitions. So we can also observe the rotational structure within the vibrational, within the electronic structure as well, if we have a high resolution spectrometer, which is pretty cool. And so now continuing along, if we continue that vertical transition up and up and up, I'm going to go like, ooh, I can't draw a straight line. Let me try that again. So if I go all the way up past those vibrational levels, you know, somewhere into here, so now we can see this is the absorption spectra from 130 to 170 nanometers, which would put us up on the scale and out of this diagram completely. We've gone past this vibronic structure, and now what we're only seeing is this what's known as continuum absorption. So we've gone past the well, so we're no longer seeing these individual vibrational states. So instead we have this nice, smooth, continuous looking spectra. So that is also very much a part of vibronic structure that we can see. So I'm going to share with you one of my favorite UV-Vis spectra. So this is a spectra of the hypochlorite radical ClO. This is so cool because it's one of these spectra that just so happens to be where the lambda max occurs right at the top of the vibrational levels. And so as we go to higher levels, we get continuum absorption. And as we go to lower energy levels, we get this banded vibronic structure, where the numbers indicate the initial vibrational quantum number and the final vibrational quantum number. So you can see up to here is indicated about 10 levels. Right here is about 12 vibrational levels. So this is pretty cool that this spectra works out to be that way. And as we might guess, if we look at its potential energy surface, we can see just that. So we see in the ground state, the Frank-Condon overlap puts us right at the top of this potential energy well. So then below this well, we have all of those vibrational energy levels, which as you can see shows up in the spectrum. Here's the spectrum turned on its side. And then above those energy levels, we're out of this banded vibronic structure. So now we just get this continuum absorption. So I think this is really cool that we can find a sample molecule that does just that, where our lambda max puts us right at the top of the well. Okay, so there's lots and lots of other molecules and their potential energy diagrams that we could discuss, but hopefully we can start to get a flavor now for why we see the features that we do in a UV-Vis spectra, particularly for gases or for molecules that have well-resolved vibronic structure. Okay, we'll continue on this in the next talk.